How's your Monday so far? Not too bad. Oh, it started out hectic. Well, it's more like get up earlier than normal, come here, do something not common. But it was for outreach. It was for a high school, and I did a bunch of demos. And so once we got started, it was a blast. And so now I feel good. It was just drudgery getting to that point. But that's a good way to start off, doing a bunch of demos and having fun, especially, when you know you're not going to be tested on it and have a final. And although their teacher was sitting there going, oh yeah, I'm going to write that down. Well, I thought we'd start right off with clickers. I chose 4 questions to review, get us back into this, remember what we're doing, check your understanding. Okie doke. Fire away. We didn't talk about this one specifically, but the book has, and I want to see if you can make the connections. So there's 2 things vibrating, obviously. Are they in sync or not? Since others are just coming in, I'll stall in. The lecture today emphasizes in chapter 20 more of this, of driven frequency versus natural frequency versus resonant frequency. I didn't see any light bulbs going off. Whoever's read chapter 20 knows what I'm talking about. And this is one where you do have an electrical signal feeding the loudspeaker. That's what's causing it to move. And then it physically moves and pushes the air around so we hear it. So, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. All right, half of you think it's both, and the rest of you are split. So over majority's right. It is both. So this is an example where almost everything, what you're trying to drive it at, the source of the waves, the vibration, that's the electrical signal telling the speaker cone to actually move. And then it's going to move at a certain rate. Well, if it's moving at that rate, that's the air it's going to push. So they're all the same frequency. If you you pulse it with an electrical signal, it moves at that same frequency. It pushes the air around at the same frequency. That's the frequency you hear. And that is how speakers work. You just send it a pulse at the right frequency, and that's how you can get that frequency sound wave out. We'll learn a little more about electricity and magnetism, how that signal makes the electrical signal makes the loudspeaker move, but we're not there yet. Does that make sense? So this is an example where the book would call it a driven frequency. You're forcing it to vibrate at that frequency, the electrical signal. All right, next I wanted... We started discussing wave velocities through different mediums, different materials, not just air. Your clue is my domino demo helped with this. So it does travel differently in different materials because they're made up differently. It's those interactions, the vibrations through the material that matter. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, you mostly think steel. You're right. In general, solids. Sound travels faster through solids, or waves in general. And think of it, they're packed tightly together. They're close, so they can have the interactions more quickly. Get through them faster. Gases are kind of lame, or at least a lot slower, because they're farther apart. So by the time you hit this one, you vibrate it, it's going to take a while before that interaction gets to its neighbor. Where in a solid, that happens really fast. Keep losing my place. There it is. All right, what does the speed of sound vary with? The wave velocity in a material varies with what? You can change that speed. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, that's a nice even distribution there. Whoosh, ramping up. So progressively, let's see, favorites are temperature or all of them. Okay, this one I want you to discuss with your neighbor. Because, let's see, most of you think temperature has some effect. But a third of you or more think amplitude and frequency are going to matter also. So do discuss this one. We'll re-vote. If you've come to a consensus, go ahead and enter your new vote, or same vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, you lose. Okay. So more of you have switched to temperature. We have flip-flopped, so I feel a little better, because it is temperature. Let me move these in case you're reading. What's it say? Although loudness varies with amplitude and pitch varies with frequency, speed is not influenced by either of those. A listener in the back row of a concert would find music confusing if sound of different frequencies reached their ear at different times. That's how I like to remember that one too. They're all playing a bunch of different notes at the same time, right? You hear them all at the same time. So frequency doesn't affect how fast it takes to get to you. That would sound really weird. Say you heard all the high ones before the low ones. It'd kind of be pointless of having a symphony. And amplitude is just how loud it is, remember? The size of the waves, the heights, not the wavelength. Now temperature, most of you agreed with, and that's because if you warm it up, it changes the medium and the spacing between the molecules or atoms. Does that help? Does anybody would like more explanation? Yes?
Just using the formula, I mean, if frequency affects the velocity of waves, so why wouldn't it affect?
The speed of sound varies with frequency. For a given medium, we're just talking, the speed of sound, it takes yay long to get to you. And it takes the same amount of time to get to you, whether I talk like this or whether I talk like this. It's the same speed. I've changed the frequency. What else had to give, though? If the frequency was different, the wavelength had to adjust. So for any given medium, Yes, you can change the frequency, certainly, but it still takes the same amount of time, or speed, to reach you. That would be the time also. The velocity is determined more by the medium, yeah. In air, it's slow compared to steel, 15 times faster. Yeah. And if we heat up the air, it'll get to you even faster. But it'll still sound like the same pitch. You guys know this. You're in a warm room and you talk, your voice doesn't sound higher like Mickey Mouse. Now, replace it with helium, right? And if you could live, that changes the wave speed, and so it sounds different too. For that case, you might be curious. With helium, in that case, you've changed the medium, so the wave speed is different. It's higher, it's faster in helium. So if that increases, at least one of these has to increase. And I bet you know which one, because you've probably done it. Frequency, because you sound like Mickey Mouse, don't you? What's staying the same then? The wavelength. You're still producing the same waves, but they're vibrating more quickly because they're traveling more faster. I think I had one more. You've been disconnected. Bueno. All right. Well, I was going to ask you this one anyway. See if you can get it right now. Go. What's the loudness of a sound related to? I hope you get this one right. Because I have so much confidence, I'm going to start counting down now. 10.
You change the session number.
It does every time it logs out, so I'll give you more time then. I forgot about that. Since it kicked us off, I had to log back in. You're right. The session ID did change for those of you using ResponseWare.
Okay.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Okay, 87% amplitude. I won't lie, I'm a little concerned about who answered A, B, and C. Can I help you? Now's your chance. Loudness does have to do with that amplitude. I hope, I know it's tough, maybe you're embarrassed, but I would like to know what you're thinking. Because somebody else, 13% of you are thinking something. You could help them, but I'm confused. Any takers? Anybody willing? Or did you just hit the wrong button, or are you playing with me because you didn't want to get it right? Okay. All right. Again, as you go through these, I encourage you, especially if you feel like you're not getting this well, the checkpoint questions in here are wonderful, especially in chapter 19. Look at the answer key to the homework you just turned in Sunday. It's available now. You can look at that. At the end of the chapter, there's a lot more practice questions, and the odd answers are in the back of the book. Okay. So we're transmitting through different things. We got different speeds. And now we're going to start bouncing it around. So the first one's pretty obvious. I won't spend a lot of time on it. Sounds reflect. We get reverberations. Echoes, as my daughter would say. Echo! She loves just shouting out wherever she can and hearing it come back. There is a law, though. The law of reflection. This is in your book. That we draw a normal. It's perpendicular to the surface. And we reference waves with respect to that. So if any of you are going on, you'll have the same consistency. And this is true for any wave. This is actually true for about anything that's bouncing, rebounding. without spin. How many of you play billiards? You're putting spin or English on the ball, or tennis, you're hitting. If there's spin, you can change things. But without spinning, and waves aren't spinning, then it is simply you have an incident wave. The one that's coming in, the initial one. And it makes a certain angle with the normal. So I bet you can guess what angle it comes out at. The opposite. Symmetric. All right. This is the reflected wave. And the angle it comes out at is the same. That's the law of reflection. The angle ins, the angle out. The Center for Science and Mathematics Education does this sports and science program, and they got some posters, and one of them they did recently was basketball. And when you're doing a bounce pass, a basic bounce pass, the angle ins, the angle out. You can put spin on it and change things, because friction will add a horizontal force. We're not going there. But that's true of waves. So when I talk and I go, echo! Yeah, the wave fronts come out, and if it comes into here, then it bounces off at the exact same angle. And off of everything it hits. And so that's acoustics. People that figure that out. Some of this wave, you might have 100% come in here. All of it towards the wall. All of it might not come out here. Where would some of it go? Heat. What would it be warming up? Yeah, the surface. And, or, the air, the medium it's going through. Yeah, it takes energy to drive that. The vibrations, there's forces, that's what's moving them. And so energy does dissipate with waves. And so you can put some really absorptive tiles, and it doesn't bounce off as much. You can kill the echo. That helps. But then the hard surfaces like brick, you get more of it. And the angles can matter. You see hulls and the things above you at certain angles. It's trying to reflect it where it should go, fix a lot of this interference so there aren't as many dead spots. So you remember when we did the two speakers? And I went like this, you might hear a dead spot. But if it is always reverberating and reflecting and echoing, and they all come to your head, chances are they'll never all completely destructively interfere. So you wouldn't have dead spots. But the reverse is true. If you bounce things around a lot, then I keep talking, I say hello, and while I'm still talking, the hello is still bouncing around, and you just hear this jumble. So you can't have it too echoey. That stinks. So there's a nice balance between that. And acoustics is simply the study of that. These materials, these angles, finding that balance. Light does the same thing. Your mirror. You look at yourself next time and you're doing a selfie in the bathroom. I don't know. You look at yourself and you can change the angle. And what do you see? You'll see something over there. You can do it in when you're underwater even. When you're swimming around. You ever tried that? That's fun. You're in the pool and you're swimming along here. Yeah, crab style, I don't know. There. So if you look up, here's a change in medium. And some of the light, depending on this angle, you can get total internal reflection. And what will you see? The fish. It's like you see an image of a fish up here. If you look straight up, you'll see outside. But if you do the angle enough, because of the two types of mediums, and the speed that the light waves travel in air versus water, that change can become such that at some angle, it'll all reflect and stay trapped inside. You can't see out at that angle. And you would see your buddy swimming over here, or a fish. And the fish would see the same thing. If you can see the fish can see you. So there's another way to bend light and waves and sound, and it's called refraction. Refraction. And that's essentially the bending of light, the bending of waves. The wave fronts change direction. They pretty much go in straight lines from, but as they're trying to change mediums, they can bend. So the idea is, if you're looking up, say, at this angle, you have a normal again. Some of it will reflect at the same angle it comes in at, but some of it will refract, and that means it goes through. But look at how it changes directions. It's like it got bent. It doesn't come out at this angle. You'd see it over here. So if you got somebody on the shoreline over here standing up, you looked up here, you'd see their face, because the light from their face would be coming, changing mediums, and it would bend and come down to your eyeball. And sound does the same thing. Here's one way to help you think of this. I got this cork and just something slicker. This is a little wheel axle that spins. And think of this as a wave front. We did that with Doppler effect. You got a source here and it sends out a wave and a wave, and it spreads out with distance. Well, if you run into where it's trying to change mediums, at some point, part of that wave front's going to be in this medium, and the other part is still in the initial medium. So kind of like this. We can start in the white medium, and as it goes forward into the cork, it bends. I'll give myself some more room here. Can you see that? So it's headed straight in front of me, but then it kind of turns. It's hard to let go of it straight. But can you see it when it switches? So when it's like this, this wheel and this wheel are not going at the same speed. So same with the wave. The wave speed changes. This one, it travels more slowly. And so if this is going slower, this one's going faster, that means it has to turn. Look at it this way. If I start like this, it'll always go that way. Even if I start this way a little bit. What if I start in the slow and go to this one? It'll still bend, but the other direction. Let's see. Go. Did you see it? It bends. That's how, if you read the story in the textbook, the author has an experience I always experience. Maybe some of you have. Oh, wait, was that in here? Maybe it was a video I saw of him. Whatever, doesn't matter. Imagine you're at two camps. You're across the lake, and you're over here having a campfire, and the other troop or something's having a campfire over here across the lake. Have you ever experienced this where it sounds like you can hear the people talking like they're right next to you, but you look and they're like really far away? And it's easier to do like over a lake at some points. Why would that be? And it depends on when. It doesn't always work. He at least has some pictures explaining this on page 357 if you want to review. But the idea is it depends on the air. We'll start with this first one. If this is warm and this is cool air, then it's like you got two different mediums. It's a gradient, of course. And the waves come out. You're talking over here. What are the waves going to do? Which one do they travel faster in? Warm. So think of the wheel as a wave front. It's coming along like this. And if this wheel can move faster than this one, which way is it going to bend? Up. So you're going to get these waves that kind of go up or the sound goes up. So in that case, these people don't hear you. That's what we normally notice. But at night, it can kind of flip. If you have the cool air down here and the warm air up above, now if you talk, which way does it bend? Down. You get the idea. So any wave that's trying to go up. And so, yeah, these people can even, it sounds like they're whispering in their tents. And you can hear them over here clear as day. Due to refraction. Because waves bend in different mediums as they're changing. Light will do the same thing. Here's one example. You know, when you stick a pencil in the water and it looks like it's bent, that's refraction. Because the light waves are changing mediums from water to air or air to water. Any questions about that? We'll do more with refraction when we get to light. All right, the energy in sound waves we started talking about. They do dissipate to thermal energy. Which ones do you think dissipate more quickly? High frequencies or low frequencies? Or does it matter? Why do you say high? What are you thinking?
Because they move, so if they have a higher frequency, they come faster, and so they dissipate a bit more quickly in a slower wave than a wave that's coming at a lower frequency.
I know what you're trying to say, yes. I'll let somebody add to that and then I'll comment.
Kind of what she was saying, like the higher frequency waves, they're doing more in a certain amount of time, so they're having more collisions with other particles around them.
Good. Between you two, you got it, yeah. Higher frequency waves are coming in more quickly. The interactions happen more often. And if they happen more often, you can get through faster. The sound. So, what was I saying? Yeah, the high frequencies will interact a lot more often. More opportunities for that energy to be converted to thermal energy and be lost. So, high frequencies don't travel as far, for example. And what do we use on the coast to help ships find their way in? Lighthouses. And for sound? What's that? Sonar to detect them, yeah, but to help guide them in sometimes. They're low for a reason, because they travel a lot farther. So they can be heard farther out, farther away, even if you can't see it. Another example is, you know, you're driving up to the traffic light, and you hear that boom, you love it, right? You turn over, and what the... Why do you only hear the bass notes? Those are the longer frequencies, right? The lower frequencies, the longer waves. Well, one reason is the higher frequencies dissipate more quickly. It's another reason too, but we're not there yet. But so remember that sound waves do have energy. Let's start driving some more things. I don't think this is that complicated. So I'll try not to dwell on it. But here's an example of this naturally wants to resonate or vibrate like this. Just based on its length, size, material, it naturally wants to vibrate that way. I can force it to vibrate at a different frequency. I can drive it. Right? So that's a driving frequency, and I'm making it vibrate. Or, you know, I can hold it and do one of these things. So that's a driving frequency. This is its natural frequency. And what happens if we match up? If I drive it with its natural frequency? Let's see, it's going up and down. Get in sync with it. Whatever. I'm always opposite. I do that. I tend to do that with music too. My friends are always, "You're offbeat." Yeah, exactly. I know you're offbeat. My excuse is when a kid, I was like, you know, whenever everybody's pounding the drums and hitting the cymbals, Well, I don't know. I think it was because I wanted to hear myself, and so they do the that way I could notice it, but it was always offbeat, and maybe I just trained myself poorly. But anyway, it was still the same frequency, right? I was just out of phase. So if we put them together, we would destructively interfere, and I'd null the music. But anyway, so if I can drive that at that frequency, it easily increases amplitude. It puts more and more energy in. That's resonance. And you know this. You've pushed your kid brother in the swing. The swing naturally, based on its length, we learned that, has a certain frequency. It's natural frequency. So if you push right at the right time, your driving frequency matches the natural frequency and you get resonance. And they can go bigger and bigger and higher. We increase the amplitude. If I drive this, there's the natural, at a higher frequency, sure, I can, but see the amplitude's not as big? Because it doesn't naturally want to, or more slowly. I missed. I'm trying to be consistent. You can see it wants to vibrate, but I'm a little too slow, so I keep messing it up. We're not matched up. We're not at resonance. You got to be at resonance. There. Whoa, crazy. And that's what instruments try to do. That's what your pop can does on your dashboard when you're driving your car, and when you've hit a certain frequency. Well, that's true, but a certain speed, your car naturally has a vibrating frequency. And sometimes the can just starts rattling, especially if you're in a country. I grew up in Kansas, so we had a lot more washboards. And you're trying to go over the ridges. You guys know what a washboard is? It's when the dirt makes the little ridges. So when it makes your car vibrate, it's driving your car and forcing it to vibrate. Well, if your car naturally wants to vibrate at one of those frequencies, you just feel the whole thing shake. Your pop can's shaking. There's two ways around that, by the way. My way, slow down. And what are you doing? You're changing the frequency. So it's not the natural frequency or the resonant frequency of your car. My brother takes the other philosophy and goes faster, which solves the problem. You're no longer because you're at different frequencies, but you're in contact with the road a lot less too, and it's not as safe. But that's my brother. So I got some things to resonate. Start with a tuning fork. You whack it. And the tines are moving back and forth that you can't see. Pushes the air and you hear it. Raise your hand if you can hear it. Yeah, but it's not great, is it? That's because it doesn't push enough air around. Is there a way we can increase the amplitude? Push more air around? You betcha. Sounding boards. You couple it to the air. So if I stick it in here, oh heck, before I do that, missed. Might even work on the board. My favorite. It's really loud to me. It literally vibrates the bones in your head and goes to your ear that way. So you can get the vibration through the air in your eardrum, but you can also just do it directly through the solid material in your head. It's a lot louder. So why? So the wood is driven, a driving frequency. At what frequency? The frequency of the tuning fork. This one's labeled at 512 hertz. So review. What's the wavelength? Figure it out. Good practice. If the frequency is 512 hertz, that's what the tuning fork wants to naturally resonate at. And I'm driving the wood to vibrate at that, so you hear the same frequency. What's the wavelength? We can use, if you forgot, the speed of sound at room temperature is 340 meters per second. See, that comes out to be 0.66. Say it again. 0.66. In the units? All right. So 2/3 of a meter. Okay, this is roughly a meter, so there. We got an up and a down. You can visualize it now, can't you? Or the compressions in the air. It's compressed here, spreads out, and compressed here, about that far apart. Very good, thank you. Here's another one. Can you hear it okay? Because I can't. Sounding board. Okay. Oh. Here's my favorite though. There's these talking strips. All right, does anybody, Barbara and Ron, help me out here, still have some records? Okay, some others do. That's why you're in Oris's class. They have ridges and grooves, and the spacing between them determines the frequency. So this has little ridges. I'll use my fingernail, and it makes it vibrate. At what frequency? The spacing tells you. The frequency is to say what's recorded on it. You guys can't hear it. If you'd like to try afterwards, this is my favorite way to do it. And I can hear it plain as day. You'll have to come up and try it if you don't believe me. But I'll use this Pi Pizzeria box to see if you can hear it now. It says Little Shop of Physics. That was the outreach program I was involved with at Colorado State University before I came here. Do it again. Little Shop of Physics. What do you think will happen if I go faster? And slower? Anyway, you get the idea. You could tape this to a cup or a balloon. It does the same thing. They even used to market things like this. They'd have a little radio unit, battery powered, and you'd put a lollipop in it. And the handle would go touch the speaker that was vibrating, and it would force the stick to vibrate at that frequency, which would make the lollipop vibrate at that frequency, which when touched to your teeth would make your teeth vibrate at that frequency, and you could hear the radio in your head. Nobody else heard it, just you. Yeah, they were cool. And how many of you have ever blown over a bottle? That's resonance. I'm causing the air to move, to vibrate, changing the pressure, right? And so air sloshes in and out. It's kind of like think of a slug of air in the neck, and it's being compressed and spread, and it's kind of oscillating in the neck. But the size of this determines the wave. How do you think this one will sound? Lower. Its natural resonant frequency is 215 hertz. Did I label this one? No. And I told you I always wanted to be in a jug band, I think. I mean, it's an easy instrument, and you don't change the pitch, right? Oh, I thought of one. How many have done your finger over a wine glass? Yeah, I forgot to bring that out. I'll go get it. So what you do is your finger sticks and slips like a violin bow around the rim, forces the vibrations, makes the glass vibrate, which makes the water vibrate. And if you're up close, you can see the ripples in the water even. You have a different cup, it sounds different. But I'm going to ask you, what do you think will happen if I remove some of the water? What do you think? Who's seen Miss Congeniality? This was her talent. She was like tuning them, and it didn't sound right, so she drinks a little less water, and then it sounded better. It's shifted one way in the movie, which is the incorrect way. They got that one wrong. What do you think? A lot less? You hear the difference? Pour it back in. So more water makes it lower. Why do you think that would be? What am I trying to vibrate? Yeah, the water. There is more of it. It's like the mass on a spring. And if I increase the mass, it had more inertia. The spring was trying to pull it and stretch it, but you get more mass, it's harder. And so it vibrates more slowly. Same idea with this concept. You add the water, and it's kind of like more mass damping it. And so it can't vibrate quite as fast, which makes a lower note. Versus. It's easier to vibrate now. It doesn't have to move the water around also. You don't even need water in it, this cup. It's the glass that's coupling to the air and making it move. This is called a photophone. Go Utes! I put a Walmart bag here, plastic bag, a little piece of reflective material on the end that's not too heavy. So it's like a drum head. And I'm going to shine a laser onto that. Hopefully it's reflecting on the, oh right behind the rope. Dim the lights, it's not that bright, I guess. It's not a mirror, so it diffuses a little. Can you guys see the green over there all right? So what I'm going to do is make a fool of myself. Oh, you know what? Move this a little closer. Oh, now it's over there on the tile, I guess. So this naturally wants to resonate. And you can see when I talk like this, la 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 la, A, B, C, blah, blah, blah. My sound waves are transmitting energy and it's making the diaphragm vibrate. And that just amplifies the vibrations. But this cone has a natural frequency that waves want to bounce back and forth at. So if I try to drive it at one of its natural frequencies, we can hit resonance, and the amplitude should increase. You can see that when I talk. Sometimes it gets bigger, and sometimes it doesn't. Okay. Oh, that was a good one there. You can tell you. La 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 la. Thank you very much. So, simple photophone. Everything naturally wants to vibrate at some frequency. Some things will resonate better than others, like a wine glass. Where this, no, but it would still vibrate. Well, I should say anything elastic. And elastic doesn't mean just stretchy like a rubber band. It has to be, it needs to spring back. We usually don't think of steel or aluminum as elastic, but clearly it wiggles and restores back. If something like silly putty, it doesn't spring back, so that wouldn't be elastic, and that wouldn't resonate. But anything that's elastic can. There is one more way to do interference. Oh, before I do that one, I want to do this one. This is coupled oscillators. The metronomes are out of phase with each other. But each one is trying to force the platform that's free to move on pop cans to vibrate. But they're all in different phases, and so they kind of mess each other up. They're transmitting energy through the board. This was a serious problem back with grandfather clocks in their day. Someone would put one in one room and another one in another room, and they would get the time off because one would vibrate through the walls on the floor and mess up the other one. And at some point, they'd be in sync because they keep pushing. Don't put, and they slowly, well, here we go. It's a lot easier if we just do it together, right? Your heart muscles do this, by the way. Right, Tommy? You remember that from Rich? He was in our physics of the human body class. And the heart muscles, it'll fire. And as soon as it fires, it makes its neighbors fire. But then they fire. And there's a little delay. But each time it refires, they're a little more in sync. Eventually, when one fires, they all fire in sync. That's a good thing. So your heart pumps together. If you take this off, or your heart gets out of sync and one's firing while the other's out of phase with it, your heart is ineffective and you die. So with time here, you can kind of start to tell already they're not coupled as well to each other. They can't transmit the energy, and they're starting to get out of phase again already. You can hear it. So that energy really is transmitted. It does couple. It's driving all kinds of things. And enough of that. So let's interfere some waves one more way and let you go. 2 more tuning forks. Sounds pleasant. Forget that overtone. You can hear that high one above it. But that versus they sound the same, right? You hear that? That's called beats. This and this are both putting waves out. Sometimes they're in phase and they add together, constructive interference, but they're slightly different frequencies. So after a moment, they get out of phase, and then they get in phase and out of phase, and that's the wah wah you hear. That's a beat pattern. And that frequency, 1, 2, 3, 4, is the difference between their frequencies. So if this was at 500 hertz, which it's not, 256 hertz, and this is at 250 hertz, what's the difference? 6. That would be the beat frequency you hear. I can change it. Let's change its inertia a little here. I'll shift this up and down a little. That'll change the frequency this one vibrates at. The beat frequency's increased. It's a higher number. So these frequencies are farther apart from each other. You can tune instruments this way. Some people with guitars do that. They'll pluck one string and another note, and they'll tune it until they don't hear any beats anymore. Because once the beat pattern's gone, they're the same frequency. I think that's right. Is it this one? Nope, next line. There's 2 lines on here. Ah, we're in tune. So that's another way waves can interfere with beat patterns. You guys got any last minute questions?
What about like making glass shatter so that once you're a little kid?
Yeah, making glass shatter is driving frequency needs to match the natural frequency. When it does, the amplitude increases, right? This will start vibrating too much and it'll shatter. And it's totally possible.